This is morning session. So our first speaker today is Andrei Negut from Massachusetts, and he will talk about categorified not invariants in Hilbert schemes.
Thank you very much for the invitation. Today I would like to speak about two papers. I wrote the authors here because I'll be referring to them quite often by their initials, so as to not write the full names over and over again. I am interested in talking about two papers which connect categorified not invariants with Hilbert schemes of points on the plane, and hopefully at the end of this hour I will tell you something about the purported connection between these 2 points of view. The only caveat which I would like to make is that what I'm giving now is actually three talks. One of them is our construction, the other one is the construction of Oblomkov and Rozansky, and the third talk would be the connection between these two. So my apologies if things will be kind of fast and survey. So I will be very light on the details, and I will be more than happy to ask any questions afterwards about details. So that's my apology for being too survey. So let me start with a construction I have with Eugene Gorski and Jake Rasmussen, and I will start with motivation. So essentially this first half hour of this talk will be just drawing a certain diagram on this board. Let's start from the type A finite Hecke algebra. So I won't go through all of the relations and definitions, but I will represent elements of the Hecke algebra as braids. So for example, here's a braid on n strands. The number of strands is the same as the number n. And the only thing I want to say about this is, as a lot of people know, the product in the Hecke algebra is given by stacking braids on top of each other. So this is the Hecke algebra with relations that I will not necessarily mention. There is a linear map from Hecke algebra all the way to polynomials in two variables. So let me write them here. This map, which I will denote by TRN, and I will define here, is called a Jones-Ognanu trace. And it's completely determined by the following properties. Well, first of all, it's a trace. So that means that if you take the trace of a product in one order, it's the same as the trace of the product in the other order. But then come a couple of interesting properties about what happens when we involve braids on n strands and braids on n plus 1 strands. So the second property is that trace of n plus 1 of the n plus 1 strand braid, which looks like this, is equal to a trace of the n strand braids sigma for any sigma. And then if you change this crossing here by the other one, so the negative crossing instead of positive, then here you multiply by this parameter A. So the observation, and well, this is why Jones and Ognanu were interested in this particular construction, is that a trace which is uniquely determined by these properties has a wonderful property that the trace of the element of the Hecke algebra which corresponds to a braid sigma is equal to the Homfly PT polynomial of the closure of sigma. So in particular, it's a not invariant because it only depends on the closure of the braid. So a couple of remarks here. First of all, it's clear that if you want to have an invariant that only depends on the closure of a braid, you need to impose this property because the closure of the product sigma sigma prime is the same as the closure of sigma prime sigma. The closure of this braid is also literally the same as the closure of this braid as a knot. The same thing is true over here, and I'm multiplying the invariant with A. So the equality I wrote here is not exactly true. You have to multiply by a certain power of A, which I will not necessarily worry about. The second small lie here is that the Homfly PT invariant, well, it depends on how you normalize it, but it doesn't necessarily live in Z of QA. It more precisely lives in Laurent polynomials, and if you want to be completely honest and very careful about your normalization, you better take rational functions. But I will just be very schematic and write everything as polynomials in Q&A, because the most important thing for me is to keep track of the number of variables in which are invariants, on which are invariants append. So this is a trace map, and this is one of the well-known constructions of the Hom-Fly-PT polynomial. And it's also one great use of the Hecke algebra, because this is a linear map on the Hecke algebra which reduces the Hom-Fly-PT invariant. Now, Hecke algebra is a wonderful structure, and it actually has a very interesting commutative subalgebra, which I will write here. So the commutative subalgebra are denoted by Cn, and it is, by definition, the subalgebra generated by a bunch of very particular braids. These braids are denoted by Li, and they are pure braids, and they look like this. So you have the ith strand wraps around all the previous strands, and nothing else happens afterwards. So these particular braids are Q deformations, or the elements they correspond to in the Hecke algebra are Q deformations of Jussi's Murphy elements, which have been well known and studied for decades, and it's an easy exercise to show that these braids commute. So you have your subalgebra inside Hn here. Inside your commutative subalgebra, you have a center of Hecke. And this is also something I'd like to write down. The center of Hecke, let's call it Zn, it consists of symmetric functions in the Lis. So note that because the Hecke algebra and everything which I have on this board are finite dimensional algebras, there will be a lot of relations in between these Lis. So in particular, L1 is equal to 1 in the Hecke algebra. And then you have a lot of other particular relations, but I don't want to bother with them right now. So the center of Hecke is inside the commutative subalgebra. This is actually a maximal commutative subalgebra, so this is why center of Hecke is inside it. And the commutative subalgebra lives inside Hn. The size of the commutative subalgebra is equal to the number of standard Young tableaus of size n, and the size of Hecke is equal to the number of partitions of size n. Okay, so this was the classical picture, which I'm sure everybody knows. Now it's time for the categorified picture. The categorification of the Hecke algebra is given by Sorgel bimodules. It's a category which I will call SBMN, and this consists of certain, I will not be too pedantic about the definition of this category, but it's the category of certain graded R bimodules. So I have to tell you what R is, which I will do here. So R is just a polynomial ring. So it's a relatively simple device, polynomial ring in n variables. And this is not just an additive category, it's a monoidal category. And the tensor product operation is just tensor product over R. And the way this looks like is if you have two bimodules M and N, so they have a left action and the right action of A, even though the concepts left and right action don't really mean that much for commutative rings, but for the purpose of representation, it's nice to think of it in this way. So if you have two R bimodules M and N, we can write them in this way, and from these two things we can produce the tensor product M tensor product over R with N, which has two residual actions of R on the left and R on the right. So it's also a bimodule. So this is the operation, the tensor operation on the category of Sorgel bimodules. So for reasons which will become apparent in a second, I will, instead of studying the category of Sorgel bimodules, it makes sense to study the homotopy category of Sorgel bimodules. Well, I will not write down complexes of certain graded R bimodules, but a gist is that this category here is a categorification of the Hecke algebra. And instead of showing you exactly how this categorification looks like, I will show you how a splitting of this arrow looks like. In other words, to describe the category of circle bimodules, it makes sense to write down a homomorphism from the Hecke algebra inside this category at the level of objects. So one can define such a homomorphism, and this is well known. You would write a homomorphism from here into circle bimodules. So if you try to just do that, you would not be very successful. The way you have to change this in order to make it work is you should write down a homomorphism at the level of objects from the Hecke algebra to the homotopy category of SBMN, and this is the reason why I took KB on the left board. This homomorphism, how is it defined? Well, you have to take a unit object in Hn. The unit object is just a trivial braid, and you have to send it to a unit in this monoidal category. The unit in the category of R bimodules is just R itself, because if you tensor with R over R, nothing happens. So this particular braid should go to R as a bimodule over itself. And now you should say where the generators of the Hecke algebra go to. The generators of the Hecke algebra are given by these braids. Well, the crossing of the I and I plus first strands, and the inverse, which is the crossing on the opposite crossing on the I and I plus first strands. And you have to say which sorgal bimodules these go to. You cannot find actual sorgal bimodules for the image, but you will be able to write down some complexes, and these are known as Ruckier complexes. This complex which is associated with this particular braid is the following. So you take R tensor R, but not over C, instead over the invariants with respect to the transposition I plus 1. So in other words, I plus 1 is the subring of R, which is given by polynomials that are invariant under the switch of xi with xi plus 1. So you have this term, and to write down a complex, the next term in the complex is just R itself, and the arrow here, it has to be a map of R bimodules, and it's actually quite simple to write down a map of R bimodules. 1 tensor 1 goes to 1, and after that, the condition that it's a map of R bimodules completely determines it. Now, for the opposite crossing, one writes down a complex where the terms are switched. So you have R here, and you put R tensor with itself over the I plus 1 invariants. So how do you define a map from here to here? Well, you have to say where 1 goes. But here you run into a small problem, because if you multiply 1 on the left by a symmetric function, it should be the same as if you multiply 1 on the right by a symmetric function in this R bimodule. So the same should be true for whatever tensor you put here. You have to write down here a certain tensor, which when you multiply it on the left with any polynomial is the same as what you get when you multiply it on the right with a certain polynomial. And after some playing around with this, and this is a wonderful exercise which everyone who has thought about circle bimodules has thought about at some point, you find that a natural choice here is 1 goes to xi tensor 1 minus 1 tensor xi plus 1. So here I have already wrote a small I on the board. So this map here is indeed a map of R bimodules, but it's not a map of graded R bimodules. The R bimodules are graded by having the degree of the variables xi is equal to 1. Sometimes in the literature people use degrees 2, but I like degree 1 at the cost of having square roots of high variables, but I'm happy with that. So if your xi's have degree 1, then this map here has degree 1. So this is not a map of graded R bimodules. You make it into a map of graded R bimodules by shifting the grading on this thing. So QR is the same R bimodule as R, but the grading is shifted by 1. That's what it means. Okay, and then by the you postulate this assignment gives you a homomorphism, and then you have to check some equalities. But it is true that any product of crossings, any braid which you can write as a product of crossings, and indeed you can write any element of the Hecke algebra as a product of generators of the Hecke algebra. That's not saying much. But the braid that is given by any product of crossings, positive or negative in any order, would go to the tensor product of the above complexes in the homotopy category of S BM. So this at least defines this homomorphism, and it's a theorem that this is a well-defined homomorphism at the level of objects in the homotopy category. So why do we study this particular category? Well, this category is a categorification of this algebra. And now let's look at the categorification of the polynomial ring. The appropriate categorification here is the category of triply graded vector spaces. And the connection, and this was observed and proved by Hovanov, is that there exists a functor from the category of Sorgel bimodules to the category of triply graded vector spaces. This functor is called KHHH, or Hochschild hyperhomology, or whatever you want to call it. And, well, you know, you can call it many things. I can sketch how it is defined. So, you know, for any car bimodule, you have the Hochschild homology functors. But the objects in this category are not just car bimodules, they are complexes of our bimodules, meaning that an object in our category is actually a complex of our bimodules. So what one does is one defines HHH by applying a functor HH to each term in this complex and stringing the doubly graded vector spaces together into a complex. So the HHH functor applied to an object here is actually a complex which looks like this. And as I said, it has 3 gradings. And the 3 gradings are the following. So gradings. One grading comes from the internal grading of our bimodules. So one grading comes from the fact that the variables xi are in degree 1. And in the business, this grading is usually denoted by Q. Another grading comes from the Hochschild homology grading, because this functor actually goes into complexes of vector spaces, not just vector spaces. So Hochschild homology grading. And this grading is often denoted by A in the business. And the third grading is the fact that we are living in the homotopy category, so our objects are not just single bimodules, they are complexes of bimodules. So what we get here are complexes of vector spaces. So we also have the homological grading. And this is usually denoted by T. So I'm writing this to convince you that the object which is outputted by HHH is a triply graded vector space. And the main theorem here due to Hovanov is that HHH of the complex associated to any braid beta, the complex of Sorgel bimodules associated by this rule to a braid beta, only depends on the closure of beta. So it's a not invariant, it's a link invariant. Okay. And moreover, to complete a picture here, triply graded vector spaces, as I mentioned, categorified this ring of polynomials just by taking Euler characteristic in the homological grading and Poincaré polynomials in the other two gradings. So this is pretty straightforward in categorification. So this is all classical stuff, which I'm sure is well known. But a thing, or at least one thing I would like to tell you about today is how to complete this picture by finding categorifications of this subalgebra and of this subalgebra. So now I will need a visible color, maybe purple. So we want to construct a category here, call it Cn, which categorifies this thing. And we want to construct a category here, call it Zn, which categorifies this thing. We also want monoidal functors from here to here, which we hope are fully faithful. So let's call this functor I upper star and pi upper star. And we want, well, pretty much everything in this diagram to commute, meaning that if this category categorifies this algebra, then this subcategory categorifies this subalgebra, and so on. So we want everything to be coherent in here. And I will actually want some more things from this diagram, but I will come back to it in a second. The main conjecture we have with Eugene and Jake is a candidate for what Cn and Zn are. So a candidate for what the categorifications of the maximal commutative of Hecke and of the center of Hecke are. So let me write it white, conjecture, GNR. The category Cn is a derived category of coherent sheaves, and I'll put it in quotes for a reason that I'll explain in a second. Coherent sheaves which are C star times C star equivariant on a certain geometric space that I will define in a second, and we call the flag Hilbert scheme. And Zn should be the derived category of actual coherent sheaves because they are now well defined, C star times C star equivariant on a scheme called a Hilbert scheme. And to define what these particular schemes or algebraic spaces are, I will start with the Hilbert scheme because it's one of the most well known. So a Hilbert scheme, Hilben, well, you know, there's a lot of definitions of this in algebraic geometry, but at the level of points, you can think of points of Hilben as being ideals I inside polynomials on two variables. So this is the Hilbert scheme of points on the plane. C of xy is the ring of functions on the plane. And we require these ideals to have co-length n. So what this means is that the quotient C of xy modulo I should be isomorphic to Cn as a vector space. So this is a definition of what the Hilbert scheme is. And it actually has a more explicit ascription, and one which is a bit more helpful into thinking about it as a scheme and working with it. So the alternative ascription of the Hilbert scheme, and this is known as a particular case of the ADHM construction in algebraic geometry, says that this algebraic variety is actually equivalent or isomorphic with the space of triples big X and big Y, which are endomorphisms of Cn, and the vector V, which is a vector in Cn, with a bunch of properties. And these properties are that X and Y should commute, and V should be cyclic for X and Y. So what this means is that polynomials in X and Y acting on V actually generate the whole vector space Cn. So this is what being cyclic means. And it's not hard to believe that you should look at such triples X, Y, and V not just as an affine space of triples, but modulo conjugation by GLN. Modulo conjugation action of GLN on the vector space Cn, which induces conjugation of X and Y and left action on V. So the isomorphism here is actually an easy but wonderful exercise to work out. Essentially, this n-dimensional vector space Cn is this quotient. The endomorphisms X and Y are just given by multiplication by X and Y, which by virtue of I being an ideal is well defined on the quotient, and the vector v is just the image of 1 modulo I. And this essentially constructs you the assignment one way, and then it's an exercise to construct it back. So this is the Hilbert scheme. What is the flag Hilbert scheme? Well, it's the same thing, but you replace ideals by flags of ideals everywhere. So F Hilbert consists of flags of ideals. So In inside dot 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 inside I1 inside I0, which is the ground ring, C of xy. So now each of the successive quotients, ik minus 1 modulo ik, is one-dimensional. So it's a one-dimensional vector space. But it's not just a vector space, it's a length 1 module of C of xy. So it's a skyscraper sheaf on the plane. So you have the option of saying where that skyscraper sheaf should be. And we ask that this quotient is not supported anywhere on the plane, but we require that this quotient is supported on the x-axis. That's an important restriction. Otherwise, our construction would not work. So this is the flag Hilbert scheme, and you have a map from here to here, which we call pi, which is a natural map that just remembers chi n. So now, yes. So the support of these ideals, in a certain sense, is the same as the ground ring on which the R high modules live. So an R high module, let's forget it's a bimodule for a second. Let's think it's an R module. An R module just means a sheaf which is supported on the x-axis times itself n times. So the fact that these quotients are supported on the x-axis means that the ideal high n, it corresponds to a length n scheme in the plane, which is set theoretically supported on the x-axis. And this is exactly what corresponds to our high modules, which are high definition coherent sheaves supported on the product of the x-axis with itself n times. That's why this is the only option which works. And having here a bigger flag Hilbert scheme which doesn't impose any restriction on the quotient would not work. In terms of this other presentation here, it's not hard to see that this definition is equivalent with pairs of matrices and the vector, where now x and y are upper triangular. So x is non-strictly upper triangular and y is strictly upper triangular. So I'll just write it like this. You have the exact same property, the fact that the commutator of x and y is 0. And then you also have a vector v and the property that it's a cyclic vector. So v is cyclic for x and y. But instead of taking a quotient modulo GLN, which would not necessarily make any sense because it would not keep x and y being upper triangular, you take the quotient only with respect to B, the Borel subgroup of upper triangular matrices. And I should say that in all honesty, the definition of the flag Hilbert scheme of length n is this thing. This thing is just the intuition. This definition here doesn't really mean anything as a scheme until you solve the moduli problem and you did a lot of things that one has to do in algebraic geometry. So this is our definition of the scheme. Okay, so this is what categories Cn and Zn are. And observe that because these are categories of coherent sheaves on something, then they are monoidal categories with respect to tensor product, but these are symmetric monoidal categories. Unlike the category of Sorgel bimodules, which is not a symmetric monoidal category, the tensor product of M with N as bimodules is different from the tensor product of N with M on bimodules. So the upshot of this discussion is that this monoidal category is not symmetric, but these monoidal categories are symmetric, which kind of makes sense on this side because Hecke algebra is not a commutative algebra, but its commutative subalgebra in the center are indeed commutative subalgebras. So because of this observation, it's not hard to believe that categorifications of Cn and Zn should be modules over some ring, or in algebraic geometry, coherent sheaves on something. And it just so happens that we believe, and from the framework we propose, it's actually quite, the flag Hilbert scheme is the only candidate which would work. But I unfortunately don't really think I'll have time to explain why that is true. So we actually conjecture more, and now I'd like to say what all of this has to do with not invariants and HHH and so on. So it kind of seems, if you look at this picture, that I'm talking about two very disjoint things. On one hand, we have these Hecke algebras and categories and the subalgebras and subcategories that we're describing, and on the other hand, we have these functors that take a braid and associate a not invariant. And until now, I haven't told you what the connection between these two pictures is. It's actually in the follow-up of this conjecture, which I will write probably on this whiteboard. So a follow-up to our conjecture is actually going to be more longer and more meaty, I think, than the conjecture itself. So first of all, as I mentioned, one expects these chi upper star and pi upper star to be monoidal functors, meaning that it respects the tensor product operation on all of the categories involved. But we also expect functors going the other way. So we expect functors, let's call them I lower star and pi lower star, going the other way with a bunch of properties, which I will now list. So first of all, I should show exactly what I mean by the other way. This should be I lower star. This should be pi lower star. So properties we expect is for I lower star, I upper star, I lower star to be adjoint, and that same for the pi's. We also expect projection formula for I lower star and I upper star. A projection formula is a good property in commutative algebra and algebraic geometry of direct image and inverse image functors between categories of coherent sheaves. Projection formula for I lower star and I upper star. And we expect the same thing for pi's. We also expect a fact that chi lower star of the monoidal unit, so the unit object in the category of Sorgel bimodules is R. We expect this to be the monoidal unit in the category of coherent sheaves, which is just a structure sheaf. So in other words, the intuition behind a map chi lower star is the following. If the category of Sorgel bimodules were coherent sheaves on something, which it's not, then you would expect the map I to come from a geometric map from something to F Hilbert, and the intuition behind how this map would look like is that it's like a birational map. But of course, all of these statements make no sense because the category of Sorgel bimodules is not coherent sheaves on anything. And we expect one more thing, which I think I saved the best for last. The functor HHH factors through all of the arrows I have in the picture. So HHH should be equal to chi composed with pi lower star composed with I lower star. So I have all the functors in the picture except for chi. Here's what chi is. It's a functor from here to here. And it's actually not very hard to imagine what chi is. So chi is defined on coherent sheaves which are C star times C star equivariant on the Hilbert scheme. And it maps into triply graded vector spaces. Chi is just the Hubley equivariant Euler characteristic. So chi is bi-graded Euler characteristic. So two of the gradings, let me mention here, two gradings come from the action of C star times C star on everything in this picture. So C star times C star, it acts on the plane, and because it acts on the plane by dilations, it acts on the Hilbert scheme of n points, and it acts on the flag Hilbert scheme of n points. And all of our sheaves which we consider in these categories in purple will be equivariant with respect to C star times C star. So the action on the plane, in this picture it's obvious. In this picture you have an action of C star times C star. The first C star dilates X, the second C star dilates Y. So it clearly acts on this space and this space, and we only work with doubly equivariant coherent sheaves on the Hilbert scheme and the flag Hilbert scheme. So this is responsible for two of the gradings. A third grading is actually comes from the fact that all of our coherent sheaves are actually have the action of a bigger algebra. So let me just write it down in words. The three gradings come from the fact that our sheaves are not just homodules, but they are modules over the exterior algebra of the so-called topological bundle. I'm sorry, I ran out of board exactly at the moment where I needed it most. So I haven't defined what a tautological bundle is. I will do it now in a couple of seconds. I just want to say that the third grading comes from the fact that everything we construct do not just have the structure of all modules, they have the structure of graded modules over the exterior algebra of something, which I will now define. But because they are graded modules over the exterior algebra of something, you get a third grading. And these two gradings correspond to Q and T in Hovanov's language, and this third grading will correspond to A. And actually, here's something which I think is cute and has not been explored, and I would love some more exploration on this topic. You actually get a fourth grading out of this business, because you also have a grading from a derived category here. What that means is the following. If you think of your invariants, of your not invariants, not so much as triply graded vector spaces, at one step up, if you think of your invariants as objects in this derived category, they will not be invariants of knots. They will be invariants of knots in an annulus. But her claim is that the invariants which you would get in this category depend on more structure than just triply graded vector spaces, because you also have the grading on a derived category here, which you lose when you take chi. If you take Euler characteristic, you lose some interesting thing about a derived category, namely where your coherent sheaves live in a certain complex. Let me remark that there is no connection between the homological grading on KB of SBMN and the homological grading on this derived category. The functor I lower star messes up homological gradings completely. It does not take homological grading on Sorgel bimodules to homological gradings of complexes in the derived category. It is a pretty wild functor. Yes?
Another symmetric monodal category you can assign to KB SBM is the Dirichlet center.
Yes.
Is that supposed to be related to the Zn?
Well, you showed me this at some point a couple of years ago. So there is a lot of literature about categorifications of the Hecke algebra, and the category of Sorgel bimodules is just one of them. Another possible categorification is constructible sheaves on B mod G mod B. And I learned from Tony and Jordi, I think that if you think of this category KB of S BIM N as being equivalent to constructible sheaves on B mod G mod B, then this category Zn should be equivalent to constructible sheaves on G mod G, where the quotient is by conjugation. So what this whole thing would be saying is that constructible sheaves on G mod G should be equivalent with the category of coherent sheaves on the Hilbert scheme of endpoints. And
that's part of the conjecture. So
no, that's what you and Jordi told me in Japan last year. And I think it's a beautiful equivalence, but as far as I know, nobody has sat down and actually done the computation behind it. And it's a beautiful theorem because it's an example of constructible coherent correspondence, I think it's called. The equivalence of categories between constructible sheaves on something and coherent things on something else. We don't really have so many examples of such correspondences, and certainly not for more complicated algebraic varieties like Hilbert. So, you know, it's an expectation. It's certainly not part of our conjecture. It's a completely different line of work, but I think it's beautiful. The only problem is that in that language, in the constructible sheaves language, I don't know a candidate for Cn. So, you know, finding a constructible version for Cn would also be a nice project. But I don't have any ideas. Well, so I told you about the so-called tautological bundles, and also told you about these braids Li, which correspond to these Murphy elements. So I should tell you what these correspond to in geometry. So let me actually write it down here. The Hilbert schemes and flag Hilbert schemes, you know, they are not just algebraic varieties. They actually have some very interesting coherent sheaves on them. And on the flag Hilbert scheme, you have line bundles. Let me call them LK. It's a line bundle on F Hilbert. And you can think of it as a line bundle whose fiber over a flag in I0 is the one-dimensional space given by ik minus 1 modulo ik. So see, in a definition of F Hilbert, these quotients have to be isomorphic to C as a vector space, but this isomorphism, as you glue along the flag Hilbert scheme, will give rise to a non-trivial line bundle. It's actually only trivial if k is equal to 1, otherwise it gives you interesting line bundles. So you have such line bundles for every k between 1 and n. On the Hilbert scheme itself, you don't have line bundles anymore because you don't have the intermediate flag, but you do have the tautological rank n bundle called T. So this is rank n bundle, or tautological rank n bundle. It's fiber over a point chi inside here, so a point in the Hilbert scheme is an ideal. The fiber is just the quotient of the big polynomial ring modulo this ideal, which we know is an n-dimensional vector space, and as you move along a Hilbert scheme, it gives rise to a non-trivial rank n bundle. So T is the particular vector bundle which appears in this business. And the reason why they are interesting for us is because the classes of LIs, so the LIs are line bundles on the flag Hilbert scheme, so therefore they are certain important objects in the category Cn. It's no surprise that they will, well, it's no surprise by my choice of notation, I guess, that they categorify the LIs. And T, which is here, so T, or the kth exterior power of T, which is actually important from what I wrote on the left board, the kth exterior power of T should categorify the kth elementary symmetric function in the LIs. So that's also part of the expectation. So we don't just say, you know, that there's a dry categorification Cn and Zn. We actually say this is where the generators of Cn and the generators of Zn should go to. And actually, our whole construction depends a lot on the fact that we are looking at specifically these LIs. So now about proving this conjecture. So we actually worked out, you know, quite a lot of formalism, and from the point of view of geometry, I think we understand it in a reasonable way. the problem is that if you want to show the existence of the functor xi lower star and di upper star with the properties we want, you have to do some computations in the category of sorgal bimodules that I personally do not know how to do. And we hope in the near future that the knowledge to do these computations will be available as soon as the paper of Elias and Hogenkamp comes up. They are, well, we'll hear Matt speak about it in 15 minutes or something, so you'll find out a little bit about what's in their paper. But I really should say that the work of Ben and Matt has been, from a historical point of view, the inspiration behind our conjecture here. So let me say exactly how that worked. It's also part of a conjecture. Well, there's a lot of things part of the conjecture which I didn't have time to write, but it's also part of a conjecture that if you look at the skyscraper sheaves called the torus fixed points in F Hilbert, I didn't necessarily mention this, but the C star times C star fixed points of F Hilbert, they are indexed by standard Young tableaus. The skyscraper sheaves at these torus fixed points, they give you particular elements of particular objects in the category Cn. And then we conjecture that if we hit these particular skyscraper sheaves with I upper star, they go to some objects in the homotopy category, which are exactly the categorified Jones-Wenzel projectors which are being constructed by Elias and Hogenkamp. And these, they are based on a generalization of the work of Hogenkamp and Abel. And I say it was the inspiration behind our construction here because we first became aware of all of this structure when and we heard and we saw from Matt, I think it was in a talk of Matt at Columbia or something, if I'm not mistaken. That's the first time I was ever aware of their construction. The inductive construction of their categorified Jones-Wenzel projectors matches the inductive construction of torus fixed points on the flag Hilbert scheme. So that's when it started to become apparent that there is a connection between these two categories, and a connection as we understand it now is there's a monoidal functor from one to the other, which would explain why the skyscraper sheaves of torus fixed points on F Hilbert go to the categorified projectors that are constructed by Elias and Hogenkamp. So that's well, that's how this study actually started, I think 1 or 2 years ago. Okay, so I have 10 minutes, which is certainly not enough, to talk about the connections between our work and the work of Oblomkov and Rozansky. So hair construction looks a lot different, but I will hopefully try and persuade you that they are actually constructing the same thing. So what do? They don't work with sorgal bimodules, but they also work with a braid group on n strands. And what they say is that there is a homomorphism from the braid group on n strands of type A to the category of to a category of matrix factorizations. So I'll say in a second what these are, but I should say that these are B times B equivariant matrix factorization on an affine space, which is Borel B times G times N with a certain potential W. So I should give you some notations, I guess. G is GLN, B is upper triangular Borel, upper triangular invertible matrices. Lie algebra B is upper triangular matrices period. So I'll just write the exact same thing. And N is strictly upper triangular matrices. And a potential W is actually, it's an interesting function on B times G times N with values in C. Its value on a triple, which they write X, G, and Y, is equal to the trace of X, G, Y, G inverse. So what's a matrix factorization? I will, well, in the interest of time, and I will ignore what it means to be an equivariant matrix factorization. An object in this category is a two-periodic complex of coherent sheaves on this space, which are equivariant with respect to this group, So it's a two-periodic complex which corresponds to arrows A and B, where the composition A tensor B is multiplication by W, and the composition B with A is also multiplication by W on the modules M1 and M2. So M1 and M2 are coherent sheaves on this affine space B times G times N. So, well, this is extremely schematically what their category of matrix factorizations is. So they say that you have a homomorphism from here into here. So essentially what they do is they write down a matrix factorizations which correspond to a trivial braid and the ith crossings either positive or negative, and they check that all the relations between them hold in this category, which is a very complicated check that takes 100 pages, but once it's done, corresponding to any braid, you will have a matrix factorization in here. So the interesting thing now is that they have a procedure to go from this category precisely to coherent sheaves on the flag Hilbert scheme. So let me explain how this works, because it's kind of interesting, I think. So let me call this map here phi, this map here psi, and say a couple of words about what phi and psi are. So what their construction gives you is for any braid beta, you get a matrix factorization phi of beta. So I'll just write it as matrix factorization of a certain space. This space here is just the affine space B times G times N with the potential W. And they also have an analogous construction which gives them phi prime of beta, which is a matrix factorization on the exact same space, but now with the potential minus W. So then they say there's a way to tensor matrix factorizations, which is actually pretty straightforward from tensoring two periodic complexes. So they say take the matrix factorization, call it C beta, which is equal to phi of beta tensor phi prime of a trivial braid. This is now a matrix factorization on, well, this space with potential 0. So if you have a matrix factorization with potential 0, it just means a two periodic chain complex. So we can think of this as being a chain complex on this space, which I'm writing with dot, dot, dot. And now the observation is, because this chain complex comes from tensoring a matrix factorization with potential W, one can show, well, one actually has to prove this, but I will write it as a note, that all partial derivatives of omega with respect to all variables, so a variable x, they stand for the affine directions in B, G, and N. The note here is that multiplication by each of the partial derivatives of W is a null homotopic endomorphism of C beta. So because of this, the conclusion is that the homology, or I should say the hypercohomology, so as to not confuse it with sheaf cohomology, the hypercohomology of C beta is a sheaf on the critical locus of W. It's a coherent sheaf on the critical locus of W, which is, well, which is the scheme that is like spec of functions on the ambient space modulo the ideal generated by all of these partial derivatives. Hypercohomology of C beta is a sheaf on this critical locus, and the observation is that this critical locus is exactly the flag Hilbert scheme. So because of this, this particular sheaf is what they call psi of phi of beta. So this is her construction. They write down a homomorphism from a braid group into an auxiliary category of matrix factorization, and they work out all of the necessary machinery for working with such matrix factorizations, because they need some operations which are a little bit technical, like convolution of matrix factorizations and so on and so forth. But then from a matrix factorization in here, there's a procedure which gives you a coherent sheaf on the critical locus, and then one observes the critical locus is exactly the same as the flag Hilbert scheme. So this is what they do. And here's what we do. So we have a homomorphism from the braid group to the category of complexes, a Hammurabi category of Sorgel bimodules. And we construct, or we conjecture, to be more precise, that one has a functor I lower star from here to here. It's natural at this step to conjecture that these two constructions are the same, meaning that the square commutes. And you know, we all have believed this ever since we spoke about our construction and they spoke about their construction, and it seemed like a lot of things were so common that it has to be the same thing. But right now, in the last 3 minutes, I want to conjecture more. So I want to conjecture that there is an equivalence of categories from here to here, or between the matrix factorizations and this category. Let's call this a new lower star. And this is a conjecture I made with Oblomkov a few months ago. Anyway, so there exists an equivalence of categories new star, which makes a triangle's commute. So why would this be significant? Well, this is significant because in the first conjecture, in the most basic one, we say we have two constructions that associate to a braid a sheaf, and they just happen to pass through different categories, but the answer is the same. With this conjecture, we actually say the intermediate categories are all the same. So what we're doing are just two very different languages of the exact same construction, and languages we have and they have are very different. So that's why establishing this equivalence of categories is a non-trivial thing. But here is the evidence for this thing. So evidence. It's actually easy to construct lower star. It's harder to show that it's an equivalence. So to construct a new lower star, look at the map. Well, it's an easy map that takes you from the affine space where matrix factorizations live, which is B times G times N, to the affine space, which is Cartan times Cartan. So H stands for a Cartan subalgebra of diagonal matrices, and it's isomorphic to Cn, as we know. The map here just takes X, G, and Y to the eigenvalues of X and the eigenvalues of G, X, G inverse. And if you have a module here, you can push it forward and get a module here. But what's a module here? It's a module for polynomial rings in 2n variables, and that's the same thing as a Sorgel bimodule. Of course, to make this precise, you have to care about the B times B equivariance. You have to care about what happens to this potential, just to show that this map is well defined. Then to show that this triangle commutes, you have to show that if you take a generator of the braid group here, it gives rise to an object here and an object here. You have to show that the matrix factorization you get here pushes forward to a Rukia complex in here. That's a straightforward check which one can do. Constructing the inverse of this equivalence, which is of independent interest, has got to be an interesting thing, because constructing the inverse means that you start with a coherent sheaf on this very simple affine space, and you want to get a matrix factorization on this much bigger space. So you somehow have to reconstruct the action of g and y just from the action of the eigenvalues of x and the eigenvalues of the conjugation of x. So the inverse of this conjectural equivalence will be a lot more interesting, I think. But once established, this would give an explanation for why our construction and their construction are the same thing. And I actually think, I mean, this is a work in progress with Alexei Oblomkov, so I think that in a reasonable amount of time, it should not be so hard to prove. I actually think that proving our conjecture directly would be much more difficult than proving it by establishing this particular equivalence of categories. But it would be much more satisfactory to prove our main conjecture directly from the work of Elias and Hogenkamp, I think. Thank you very much.
Any questions for our speaker?
I noticed your functor for the elementary symmetric functions in Zn.
Yes.
There was, it corresponded on the categorified thing in this rather nice thing for
that's the expectation.
For T. Is there something nice in this context that corresponds to the power functions?
I mean, I'm not sure I can say much more than just saying that any Schur function in the Li's would be categorified by the corresponding Schur functor in the Tn's.
Yeah.
And that's but that's not really saying much more than what I wrote on the board.
There isn't some nice construction.
No, I mean, I don't know of any. I don't know of anything.
Apply the Adams operations or something of that sort.
So I do not have a geometric understanding of the Adams operation other than just saying it's the Adams operation on the vector bundle.
Okay. I mean, because of the background that on the knot theory front, those ones have got a very nice way of looking at them.
That is true.
So, I mean, in this sort of picture with the coherent sheaves on the Hilbert scheme, does the Procesi bundle play any kind of special role?
I would love to understand how it fits in with the flag Hilbert scheme, to be honest. So, well, by experimental reasons, we believe that pi over star of O should be related to a Procesi bundle. Maybe something like the Procesi bundle restricted to a certain part of the Hilbert scheme, like to a Lagrangian inside a Hilbert scheme or something. But I would not know how to prove that, unfortunately. And I'm also not really sure, or at least I'm not really sure yet, what this has to do with the BKR isomorphism, which says that the category Zn is equivalent with coherent sheaves on the orbifold, which is kind of analogous, which is kind of equivalent to your question, I guess. So I do not know, and I would like to know how the Procesi bundle interacts with the flag Hilbert scheme.
Maybe another short question.
So does the existence of new star let you see that the sort of Oblomkov-Rosansky invariant is the same as the original Povanov?
In a sense, yes, because his construction, which I sketched over here, so take an object in this category and tensor it up with some other object or minus W and look at this particular chain complex. This is like taking Homs from a unit object into your phi of beta. And this is exactly what we do to get our invariant, and not just we do, this is exactly what Hovanov initially did. He said, look at the object of this category which corresponds to a braid, and look at Homs from the unit object into that braid. So in a certain sense, once everything is matched on this side and on this side, on either side, to get your not invariant, you should take Homs from the unit object into the object corresponding to beta. But saying this precisely actually involves understanding how these functors look like on matrix factorizations. The devil is in the technical details.
Okay, there seems to be no further questions, so let's thank the speaker.
Thank you very much.
For the nice talk. And we continue in 30 minutes.